We expect our machines to execute their plans flawlessly. Picture a traditional drone flying along a pre-programmed path through a dense forest, right up until a sudden, violent gust of wind disrupts its trajectory. In moments like this, legacy drones typically freeze up or crash. They rely on playbooks that assume environmental conditions will remain stable. This highlights the primary constraint in robotics. The chaotic physical world refuses to mimic a pristine, predictable laboratory. Traditional systems attempt to compensate with massive data. They require the entire environment to be strictly mapped out and downloaded before their rotors even start spinning. A new architecture developed by Aerial Robotics, called the Aerial Drone Operating System, or AIOS, moves away from this requirement for total pre-programming. To build a robot that survives when its initial plan fails, engineers abandoned the strict instruction manual and designed a system built to navigate unpredictable spaces. Watch an advanced drone running AIOS enter that same turbulent forest. As the wind hits, it physically braces and adjusts its tilt in real time. Instead of trying to guess every possible physical disruption in the universe, the system is encoded with simple, survival-based logic. The programming relies on two rules. First, collisions must be avoided. Second, planned actions might fail. By treating failure as a mathematical probability from the start, the machine doesn't force a broken script to execute when it hits a sudden downdraft. It transitions into a state of continuous caution, navigating the physical reality immediately ahead. This shift means the drone remains operational and reactive, even when its intended path is blocked. Consider an urban logistics network where wild variables appear instantly. Picture an unpredictable window washer swinging out from around a skyscraper into the flight path. To handle this, the drone's perception shifts. It stops viewing the city as a fixed map and begins calculating fluid likelihoods. In real time, it generates a probabilistic representation of its immediate surroundings. The system continuously calculates the mathematical probability that a specific pocket of airspace is clear versus the probability that it is blocked. This constant calculation allows the drone to ignore outdated, static 3D city maps that were generated hours or days prior. Surviving the unknown requires a machine to stop trusting fixed certainty and map the world based on real-time probabilities. Processing these probability shifts hundreds of times a second avoids the common pitfall of a drone lagging or freezing while trying to compute its next move. AIOS uses an engine called active inference. This process operates as a continuous loop: generate a map, infer actions, and fulfill goals. It uses this loop to actively seek out and minimize environmental uncertainty, converting the unknown into actionable data. The drone mathematically samples the chaos of its environment to determine the safest possible action, rather than guessing based on incomplete data. Legacy systems struggle here because their perception, planning, and control modules are siloed, requiring data handoffs that slow down the reaction to an obstacle. AIOS unifies perceiving, planning, and controlling into one integrated loop. By removing these internal bottlenecks, the system solves for the safest path in a fraction of a second. When the drone encounters an urban hazard in mid-air, it executes an evasive maneuver with fluid precision. This architecture allows autonomous machines to move beyond the controlled conditions of factory floors. It enables them to venture into unmapped wilderness, handling complex elements during GPS-denied search and rescue operations. They can navigate the unpredictable and turbulent drafts generated during commercial wind turbine inspections, and they can weave through the constantly shifting variables of automated urban delivery networks. When machines are programmed to navigate uncertainty rather than ignore it, they can operate in environments once considered inaccessible to autonomous flight.